Welcome viewers, I am Professor Naved Ahsan from Department of Civil Engineering, Jamia Millia Islamia, and in this lecture I will talk about various techniques of image transformation that we use in remote sensing analysis. Viewers, you might be aware that the data that we obtain, particularly in the multispectral satellite data, we have the potential available for carrying out different operations, mathematical operations on the remote sensing data. This potential provides us as well as facilitates us to transform the images into a new image altogether, which will give us better interpretation of the data as compared to the raw image. It has a wide application in different fields, for example, forestry, agricultural, study of water bodies, as well as in geological studies. Various techniques that we use for image transformation includes arithmetic operations, which may include addition, averaging and subtraction of images from one to the other. Then we also have techniques for band ratioing, and we can develop indices using ratioing as well as arithmetic operations. So, various indices have already been developed, some of them we will discuss in this lecture, and analysts may also develop their own indices depending upon their experiences. In addition to that, we will also talk about principal component analysis technique for image transformation as well as tasseled cap transformation technique. We will also talk about Fourier transformation technique for image transformation used in remote sensing analysis. So, let us now begin with arithmetic operations that have to be carried out on remote sensing data. These operations include addition, averaging and subtraction mainly. Addition and averaging may be carried out on two different images that have been properly co-registered. This analysis may also be carried out on two different bands of a same image. So, whenever we have to carry out addition or averaging, it has to be carried out on a pixel by pixel basis. If for example, we have data available for two different images in the form that here are some of the pixels taken from an image, and these pixel values have, suppose, some values 58, 60, 63, 50, 'So this is a portion of a particular image or one single band of an image. Similarly, we have data from other image or the other band of the same image. If we are applying the addition or subtraction or averaging on two different images, then we have to properly co-register the image. So, for the second image or second band, let us say the data is, again we will take the corresponding pixels here, where the values may be, let us say 48, 52, 50, 61, then 40, 57, 32. Now, if we have to carry out, for example, averaging, then we will do that on a pixel by pixel basis. In that case, we will take each pixel in the first band or the first image, and then corresponding pixel of the second band or second image. We will take the average of these two values, which may come out to be as a fraction, but that we can convert into an integer. For example, if we take the average of this 45 and 48, the average must be 46.5. But we can take that as an integer value, and we can say that the averaged image would contain this pixel value equal to 47 here. Similarly, we can also carry out the operations for other pixels. For example, here 49 and 52, the averaging must be 50.5, so we can make that as 51. Here the average must be 54 and then 61 and so on. So in this fashion we can carry out the averaging. We can also carry out, if required, the addition. Averaging may help us in removing the noise from the pixels, particularly in case of radars. If we use two different radar data, it can remove speckles from the radar. So similar to this addition or averaging, we can also carry out image subtraction, which is considered as one of the most appropriate method for particularly detecting the changes in remote sensing data or changes in the Earth's surface features. So for image subtraction, again we have to carry out the subtraction on pixel by pixel basis, as we have discussed this example. Similarly, here if we carry out subtraction process here, we will get the pixel values for this particular pixel. If we subtract this image from this image, we get the value here as -3. Similarly, in this case also we get a -3 value. Here we get a value of 8 and -1. We get +1 here, then we get -10 over here, then -2 and -1. So in this way we can find out the difference of the two images on pixel by pixel basis. Now here the interpretation of this data would give us information about the changes in various Earth's feature. For example, we can find out the change in the forest cover, how much forestation or deforestation has taken place over the given different period of time, if we use two different images of two different time periods. We can also use this method in other analysis also. For example, determining the urban sprawl changes. We can also apply the same method in case of geological studies for determining the weathering of the rock, extent of weathering of rocks. Now here the minus values and plus values, they indicate the direction of change. A value of 0 or close to 0 would tell us that there is no significant change that has taken place. So after this arithmetic operations, there is another kind of arithmetic operation which is band ratioing or development of indices, which is very widely used in remote sensing analysis. We can derive much more information using band ratios or band indices, and it has a wide application in the field of forestry, ecology, aquatic studies as well as geological studies. We can also avoid effects of terrains and slope aspect, effect of different angles of sun, if we make use of band ratioing in remote sensing analysis. For example, if we have a terrain here, now if the sunlight is coming from this direction, this particular portion may be a sunlit portion, whereas this portion may be a shadowed portion because of the slope in the area. Now, suppose we have two different types of land features here. One is deciduous trees and other is coniferous trees. Now, the value that we obtain here for both of these in remote sensing data, because of different sunlights or illumination upon the earth surface, we may not get sufficient distinction in the data to find out whether it is deciduous or it is coniferous land feature. So, in that case we can make use of band ratios. Now, suppose here we have deciduous trees here and some of the coniferous trees over here. Similarly, here we also have land features with coniferous trees over here and then deciduous trees. So, this different in the illumination in remote sensing data we can observe here in this table, where we have two different land cover features, that is deciduous as well as coniferous, and two different kinds of illumination, one is sunlit and other is shadowed. Now, as we can see in this table, the DN values that we obtain for deciduous trees in sunlit area are 46 in band A and 51 in band B, whereas for the same deciduous trees in the shadowed area the DN values are of the order of 18 and 20. Same is the case here in coniferous land features. Sunlit area we have band A 30, band B 45. In shadowed area for coniferous trees we have DN value in band A as 10, whereas in band B the DN value is 15. Now, since they are very close to each other, 45 for sunlit coniferous in band B, 46 and 51 in band A and B for deciduous trees. So, it is very much likely that remote sensing analyst may identify both of them as same features, whereas it is not true. But if we look at the ratios of these bands, for deciduous trees in sunlit area, the ratio of band A to band B, that is 46 divided by 51, comes out to be approximately 0.9. Similarly, in the shadowed area also, the ratio of band A and B is all equal to 0.9. So, we can say that the ratio of band A and B is not varying depending upon the illumination of the land feature. Similarly, we can also notice here in the case of coniferous trees, the ratio of band A and B is 30 divided by 45, which comes out to be 0.67 for sunlit areas, and for shadowed area also it is 0.67. So, in both the cases the band ratio is not changing and it is giving two distinct classes with band ratios being distinctively at larger difference. So, similar to this band ratio, we can also develop various indices. Some of the indices have already been developed, which can be used for different kinds of studies, and the common indices used particularly in case of vegetation studies are NDVI, that is normalized difference vegetation index. Then we also have SAVI, which is soil adjusted vegetation index. We also have transform vegetation index. Then we can also develop perpendicular vegetation index. Apart from these vegetation indices, we also have normalized difference in snow index, which can be used in snow studies, and also we can have indices which may be used in geological studies, that is iron oxide index. Now, let us talk about briefly for each of these indices. NDVI index is represented as the ratio of difference of pixel values in near infrared and red bands to the sum of those pixel values in near infrared and red band. So, mathematically we can write this as So, it is simple the ratio of difference to the sum of the pixel values in two different bands, that is near infrared band and red band. Now, this value will range from -1 to 1, because if we consider the maximum value for the red band as 255 and minimum value for infrared band as 0, so it will come out to be -1, whereas in the opposite case, when we consider maximum value of near infrared band as 255 and minimum value of red band as 0, it will come out to be +1. The vegetation studies involve analysis of this NDVI data, and a value of 0.3 to 0.8 of NDVI gives that there exists vegetation. We can further analyze this as NDVI ranging between 0.6 to 0.8 as healthy vegetation, whereas 0.3 to 0.6 of NDVI value represents sparse or stressed vegetation. The negative values are generally associated with the clouds, water bodies or snow, whereas values which are close to 0 or 0, they represent bare soils. The next is SAVI. This is soil adjusted vegetation index, which is nothing but a modification of the NDVI. We have same components that we use in NDVI. So, here we introduce one constant in this SAVI, that is m, and we add here m and then multiply this entire with 1 plus m. Now, this m is a constant which adjusts the index for different conditions of soil. For intermediate soil, the value of m is kept around 0.5. If m is equal to 0, then this SAVI becomes simply NDVI. Then next is the transformed vegetation index, which is again a modification of NDVI, where we can write this TVI or transformed vegetation index as viewers, you may notice that again this is modification of NDVI, but this is more correlated to the vegetation biomass, and therefore, it is commonly used for assessment of biomass on the surface of earth. So, another vegetation index that we use in remote sensing analysis is perpendicular vegetation index. This index may be developed by constructing a scatter plot between the data available for near infrared band and red band in the image. If we construct this scatter plot, we will see that the bare soil will show a linear relationship, and as we move towards the left top corner of the scatter plot, we will go towards the vegetation point. So, if we look at the plot here, we have on the x axis red band reflectance, and on y axis we will have near infrared reflectance. So, a scatter plot would contain different points like this. So, this line AB represents the soil line with different wetness or different moisture conditions. As we move away from this line towards the left corner, the vegetation, we reach to the vegetation point. For example, if we consider this point here C, and we want to develop the perpendicular vegetation index for this point, we will drop a perpendicular from C upon line AB. And the length of this perpendicular will give us the value of perpendicular vegetation index. Then next we have index which is used for snow studies, that is normalized difference snow index. Again, this is similar to the NDVI. The difference is that here we consider the other bands which are not used in NDVI. So, in case of NDSI, we make use of short wave infrared band as well as green band, and we take difference of these bands, and the formula can be written as NDSI equal to which is again the ratio of difference and sum of the DN values obtained in green band as well as in short wave infrared band. So, again if we compare this NDSI with NDVI, there is only the difference of bands that we are using. The equation remains the same. Now, for iron oxide, we have a very simple index which is nothing but the ratio of two bands iron oxide index Dn red over Dn blue, which make use of red and blue bands. So, this iron oxide index is simply the ratio of Dn values in red and blue bands. Higher the value of ratio, higher would be the content of iron oxide in the rock masses. Now, next analysis that we also carry out in image transformation, it is based upon principal component analysis. Viewers, you might be aware that the remote sensing data in multispectral forms contains lot of redundancy in the data. There is a large corroboration in the data available in different bands. Principal component analysis helps reducing that redundancy and it makes computations easier. Principal component analysis can be carried out by comparing the data obtained in different bands. If we plot data for two bands, for example band A and band B, if both the bands are in complete collaboration or they are completely correlated, then their relationship should be a straight line. But sometimes this may also deviate from here. Even in that case, if we look at this scatter plot, we will find a major axis, this line, although it may not be a completely correlating line, but it will be a major axis that can be considered for this entire set of data. Now, this major axis is termed as principal component, and an axis which is perpendicular to this is the minor principal component, and this will be the major principal component. Now, instead of analyzing the data for these two bands, if we rotate our data, if we rotate our axis in such a way that they coincide with these principal components, then certainly the redundancy in the data will be reduced and computations will become easier. So, viewers, after principal component analysis, there is another technique, that is tasseled cap transformation, or it is also known as Koch and Thomas transformation or KT transformation, which is named after their developers. This technique relates different ages of crops with the band values. There are four components which are considered, that is redness, greenness, yellowness and non-such. Non-such includes the noise in the data. As we can see, the matrix which is given by Koch and Thomas, they have suggested certain weights for different spectral bands and for different components of the crop. These can be compared as here BR, BG, BY, BN, where these being the redness, BR being the redness, BG being the greenness, BY yellowness and BN is non-such or the noise in the data. Then here B1, B2, B3, B4 are 4 different bands of the multispectral image. W is a weight function which has been suggested by the Koth and Thomas, and they have suggested weights for these brightness, greenness, yellowness and non-such. For example, for brightness the value of weight is 0.433 for band 1, 0.632 for band 2, 0.586 for band 3, 0.264 for band 4. And similarly the values of weight for other bands are given. We can now relate, if we multiply these weights with the band values available in the band, then we can find out the values of greenness, redness, greenness, yellowness and noise. Now this method is called tasseled cap because if we plot a 3-dimensional scatter plot between red, green and near infrared band, it gives the feature space plot which takes form of a tasseled cap. In this case the base of the tasseled cap is the plane of soil, and as we move upwards we move towards the aging crop, that is yellowing stuff. A bend towards the green shows the yellowing stuff finally here on the tasseled cap. There is another modified version of this KT transformation that has been suggested by Christ and Saikon. They have suggested another weight table which includes 3 components. First is the brightness, then greenness and wetness, and the weights have been suggested for all the 7 bands of the Landsat Themitra map, that is TM1, TM2, TM3, TM4, TM5 and TM7. For brightness, as you can see here, the weights are 0.3037, 0.2793, 0.4343, 0.5585 and so on. And similarly the weights of greenness and wetness are given, which can be related to find out different stages of the crop. Another technique which is nowadays being used in case of image transformation is Fourier transformation, where a spatial domain is altered or transformed into the frequency domain. This Fourier transformation analysis helps in removal of strips, vibrations and other kinds of noise from the remote sensing data. So now let us summarize this lecture. Viewers, in this lecture we have studied about different techniques of image transformation that are commonly used in remote sensing analysis. These techniques that we have discussed include various arithmetic operations such as addition and averaging of images, both spatially and temporal images. We have also discussed about various band ratios as well as indices that we commonly use. For example, we have discussed NDVI, normalized difference vegetation index, we have discussed about snow index, we have discussed about iron oxide index. Then we also discussed about principal component analysis technique, which is very much widely used technique in remote sensing analysis and helps in reducing the redundancy in the remote sensing data. We have also discussed here the tasseled cap transformation, that is the Koth and Thomas transformation technique, which provides information about different ages of the crop. And finally we also discussed about Fourier transformation technique. I hope viewers would be benefited with this lecture, and with this I end the lecture, and thank you all.